Good evening, ladies and gentlemen, and welcome to the 19th public lecture hosted by NUS Cities. Before we start, may we request everyone to either put their cell phones on silent or power them off? Thank you. For those who don't know about NUS Cities, we are a university-wide, multidisciplinary, open and inclusive collaborative platform hosted within the College of Design and Engineering, otherwise known as CDE. Through our collaborations with local and international institutions, we hope to create synergies that extend within as well as outside the NUS. The NUS Cities Public Lecture Series will investigate policies, ideas, and projects developed by urban experts which aspire to create sustainable, resilient, and livable cities. Through the lecture series, we hope to create a platform for discussion, retrospection, and conversation to give momentum to the existing research and concerning cities. My bad. I would now like to introduce our speaker for the evening, Prof. Arno Schleuter. Prof. Arno is the Professor of Architecture and Building System at the Institute of Technology in Architecture, otherwise known as ITA, at ETH Zurich in Switzerland. He is also the Director of the Zurich Hub of the SEC Future Cities Lab, the PI for the Powering the City module, as well as the Director of Studies of the Interdisciplinary Master of Integrated Building Systems, otherwise known as MIBS, at ETH Zurich. With his research groups in Zurich and Singapore, he's the author of more than 100 scientific papers, including publications in leading journals such as Nature Energy, Energy and Buildings and Sustainable Cities and Society. Recent awards include the Swiss Arc Award 2022 and the Award d'Or 2023 for Excellence in Energy Innovation from the Swiss Federal Office of Energy. Prof. Schleuter researches systematic approaches to decarbonizing buildings and cities, exploring new methods and techniques for analysis, design, and decision-making. Please join me in welcoming him.
Great. Thank you very much for this very kind introduction. Thank you very much for the invitation. It's great to be here, and I'm very humbled to have you all attending at this late hour. And I think we're at the right place because we share something. We share a fascination for cities, and not only for cities, but for cities as complex, sometimes complicated, socio-economic, socio-technical, ecological systems. Still need to adjust. Now it works? Okay. And that already denotes three different lenses you could have on the city as a system. And what makes it, of course, challenging and interesting is this intermediate part where we have all those domains interacting. And all of you that work on cities and that work on buildings in cities know that these things are tied together and they create their own dynamics and their own interactions. And this is actually what we're interested in. Then in addition to those different spatial scales, we have the question of temporal scales. So the fact that cities don't really have a start and they don't have an end, very different than buildings, which are usually planned for maybe 50, 60 years. Cities are open-ended systems. However, temporal scales become really relevant because they all happen at the same time. We can think about things that are happening in milliseconds as well as in decades and hundreds of years. And all those things are jointly present when we think about cities. And NUS Cities has been pioneering also research and discussion about complex cities as complex systems. And of course, if you look at urban science and complex systems research, we have learned that cities have very interesting traits, very positive traits. Cities boost innovation, they boost ideas, the number of patents, the economy, the cultural dimension. This is all something that is scaling extraordinarily in cities. We know that, and this is why cities are so exciting. But we also know maybe a little less, but we have to face it. We know about the negative effects of cities, and that is, of course, that also 80% of global greenhouse gas emissions are somewhat associated to urban regions. We have the issue of pollution that, despite our collective reception, is the number one source of artificial deaths on this globe. We have the question of loss of biodiversity. We have urban heat, which is pronounced by cities and their buildings. Time-wasted commuting when we choose organizational forms that are very heavy on transportation mobility. So everything would be great if we just stop at the left side, but we also have to face the right side, and I think that makes it interesting. How can we think of cities where we keep the left side and even boost it, but not only mitigate the right side, not only make things less worse, but ideally to create cities that in the future are maybe positive, even better than the environment, the surroundings, and that actually contribute to health, to well-being, and livability. And this is kind of the frame I want to set with my little talk today. And it's not moving. Here we go. I hope you don't have to do this every time. Okay. So now it should work. Thank you very much. So I want to introduce the concept of systemic design as an approach for buildings in cities, so already one particular lens that we're interested in. I want to illustrate this concept and some insights using examples from our research in Zurich and Singapore, so the work we've done on this topic. I want to address 3 of the key challenges that cities face, and that's the question of growth, of energy supply, and of materials and resources. And I want to discuss questions of process. Already before this lecture, I had some interesting conversations about how do we actually do this? What is the process behind? What are benefits and challenges? And how can we use digital tool sets to essentially get these type of knowledge and decision-making into the actual world of planning and the world of realization? Unfortunately, it's not working. Oh, now it's working. Okay, perfect. So the key question for us, for our research, how do we integrate different interacting domains in urban contexts to achieve a more holistic perspective? How do we generate and derive knowledge through science and evidence through application? How can this be used to design future cities, as mentioned, that are not only less bad, but positive? That means hopefully better than the surroundings. So our lens on this challenge hinges on 3 points. And the first one, of course, we're all aware climate change is happening. This is no news, and we're all in the same picture. Most of you probably also know the contribution of buildings to this question. 40%, almost 40% of global greenhouse gas emissions are somewhat associated to buildings. What is interesting here is that it can be distinguished between the direct emissions through consumption, direct and indirect, through power consumption and maybe combustion in buildings themselves. But also, of course, in terms of material and resource consumption. So it is fair to say that buildings make the biggest part of global greenhouse gas emissions, and this is why we need to act. So one goal definitely for us all needs to be to move towards low or even zero total carbon buildings, and I will later show an approach how we might go in this direction. A second, even similarly important, and in the past years due to the geographical crisis, even maybe somewhat more challenging, is the question of facilitating the energy transition. Our society needs to needs to change into renewable energy generation. And it's quite interesting. This is the image of the Swiss Federation. This is the plan until 2050. And you can see here that in 2050, we're supposed to have a vast amount of renewable energy creation that will take over coal, fossil fuels, even nuclear power. And you see this yellow part, and this yellow part is nothing else than solar. And then, of course, if we think about solar, it becomes clear that solar is a spatial question. So the question is, which surfaces, which spaces can I activate to actually do that? Is this within buildings, or is this, for example, in the countryside? We had very fierce debates in Switzerland if solar plants should be in the alpine regions, right? Think of the Swiss mountains, and there's large solar plants there. Some people like this idea. More people don't like this idea. But then again, there is ski lifts, there's other infrastructure, so it becomes a tricky question. Just recently, the Swiss population has actually voted against many of those plans, which then leaves the question, where should you actually put it, right? And it's very clear that buildings offer surfaces, buildings offer sealed surfaces, and there is a lot of them available, and they can offer a potential remedy to this question. So buildings have this dual role. They can generate, but they also consume. And of course, this is very much connected. So buildings as positive prosumers ideally contributing to supplying energy also for other applications. The third is, of course, adapting to climate change. I think we are unfortunately beyond just mitigating. We also need to adapt. We need to get our environment to a state where it can be protective against health hazards. And we see that, of course, our building stock is a huge factor in this. This is Zurich. This is not Singapore. This is Zurich. And also Zurich has an urban heat island effect of up to 6 degrees C in a summer night. Meaning all the buildings around the Zurich main station, this is the highest dense. It's nothing in density compared to Singapore. But this area, which is heavily sealed with a lot of construction, it gets 6 degrees warmer, which means immediately it becomes dangerous for people that are vulnerable, that are of a certain age, or have health issues. And this is, of course, increasing. So the question is, how can buildings provide healthy conditions inside and outside and can protect people from urban heat? So not only reverse this, because we cannot reverse the fact that temperatures are already rising, but how can we actually make buildings and environments in a way that they contribute to better living situations? And we see examples of this, for example, in the US, where buildings actually play the role of becoming cool centers, where, for example, public buildings are opened on the weekends because they are actually air conditioned. Of course, that's maybe not the way we want to do it, but it shows that the role of building already changes towards hosting people and protecting people from urban heat. So this is our lens. These are the three things that we mostly care about in our approaches. It's a very specific lens. Of course, you can talk a lot about other things. We're currently also bridging this, for example, to social economics and more social questions, which is a very interesting overlay. Who actually is affected by heat? Who is affected by solar plants and by emission questions? So this will be the next level for us. What also makes it very interesting, and I believe we have a lot of architects in the room, and when we started this topic, we tried to frame it and thought, okay, well, it's actually just about multiple buildings, right? It's maybe about a neighborhood. But then when you start working on this, you see that there's all those interdependencies between the different temporal and spatial scales. So if I started a building, I mean, a building is something I can look at, but of course, immediately questions about the building components rise, and from the components, I have questions about the materials. And right now, for example, materials research is very active, new materials coming up. And if we do the entire chain, we see that this actually trickles up, and I will show you an example how this can trickle up to the city scale, and vice versa. What is a building? What is the difference between a building and a district and a neighborhood? Is, of course, all the intra and inter-building effects that happen on the district and neighborhood scale, exchange of radiation, shadowing, infrastructures, district cooling, district heating systems. And then if I scale this up even once more, I end up in the city, and the city, of course, sets all the boundary conditions, the grid, the larger scale infrastructures, which immediately affect this and this level. So it's a tricky question, right? It's a tricky question how we combine this in a way of understanding this with respect to different spatial scales and temporal scales, as already mentioned initially. So how are we trying to do this? We try to address both qualitative and quantitative, but I think the novelty is for us to introduce more quantitative means. And this happens by building computational models here on top that are multi-scale and multi-domain. So we try to build basically a selection of models that help us to isolate a question and maybe answer a specific question, or at least have an insight about the mechanics behind. We all know all models are wrong, but some are helpful, right? As George Box, the statistician, has quoted, and I think that's very true. For us, this means starting working with stakeholders, starting to create scenarios. So one way to predict the future, we don't know the future, but one way to at least have possible futures is to think about different scenarios. And none of those scenarios will be the future, but the scenarios might kind of span a certain range where there's some elements that could be a potential future. So it starts with interacting with stakeholders. This can be communities, this can be industry partners, this can be other domain specialists, starting to create the scenarios. And for those scenarios, we, as a next step, then try to gather input data that helps us to populate the models that we build. Very important step is the creation of so-called archetypes, and I will talk about this a little later. So representative of buildings in cities, representative of certain things that repeat in a city. Then when we have these models, of course, we populate them with input data. We run simulations of different sorts and different ways of doing that. And then afterwards, when we have data, we try to analyze this, and then the loop starts again, and the conversation with stakeholders also is informed by that or informs the entire process. So I believe personally that to do this type of research, we need to do research, the translation, and back. So it means that application in cases, in scenarios, inspires and drives new problem sets. So we need to close the loop. Computational models can be extremely helpful to simplify certain aspects of the system. But we're essentially not interested in numbers so much. It's not about the number, because the numbers will be wrong, as mentioned. And any precision that is there is a false precision, because there's so much uncertainty in the system. It's impossible that these numbers are really true. But the models help us to identify the different interactions, to understand the mechanics, which parameter influences another parameter, and this allows learning. So at the end, if I do this, I might understand my system under my perspective a little bit better. And if I do this multiple times, I'm starting to build heuristics. So essentially our aim would that be that at some point you even don't need these models anymore, because you have a deeper understanding of the system, the underlying system. Already mentioned, we want to extract knowledge, but then when we apply it, we want to derive evidence. We want to know that it's actually true, and that's quite tricky actually on an urban scale. Buildings you can measure and monitor, you can somewhat grasp as a system, but of course larger scale systems are really hard to get the ground truth. How should we do that? This is an exciting part of research, and we had some interesting discussions actually today about that. And yeah, the specific focus I already talked about. So, of course, that's a work of many people. I'm standing here and are allowed to tell the story, but there is, of course, a big team behind. Since 10 years, we are also here in Singapore at the Future Cities Lab, with also our collaborators here from NUS and NTU, and many people that have been involved in this research, and obviously they're a big part of that. Good, let's start with the question of growth. So, a few years ago, there was one of the largest research projects in Switzerland that brought together different entities to think, how would Switzerland develop and how would you decarbonize Switzerland? And there was a lot of researchers on mechanical and energy systems behind, but it was very unclear how would Switzerland even develop and what would be the future energy demand. Everyone was developing technologies, but the question was, okay, what is actually, which type of energy are we talking about and how much do I need from this? So we started this project assessing the energy demand of future Swiss districts under urban development and climate change, and that is already something that is essential. So it's not only about assessing energy at a certain point in time, it's the question, how does it change? How does it change under urban development, so assuming that Switzerland will grow, and under climate change, which is already happening. This is just one example that the heat days will be rising quite so also in Switzerland. But first of all, growth in very concrete numbers in Switzerland means, okay, Switzerland is growing. You can see here in somewhat around 2000, we were like 7 million, and now we just passed the 9 million. So there's a strong tendency to grow. And this different projections say this will keep on going. So that, of course, causes questions of densification, of building new, and Switzerland is trying to avoid this question of sprawl, that all of a sudden entire Switzerland becomes a huge carpet of little buildings. So the questions of densification and of soft densification. So trying to rather arrange, reuse, adapt to those different measures. But it's not only the growth in people, it's also the growth in space, right? You see 1970, the average Swiss person had 27 square meters of living space, right? Now we're at 46. This is almost double already, right? So each individual person requires an average 46 square meters to be built. That's quite heavy, and of course this multiplies this fact that we need to house more people. But also in the mobility end, you can see in 1970 it was a little bit more than 200 cars per 1,000 people. Now we are above 500 cars per 1,000 people. So all these factors multiply and becomes essential how we deal with this in the future. So now you could say, well, Switzerland is a pretty cool country, not so much issue with climate change, but then if you look at the recent research, this is a paper from Nature, actually, Nature Sustainability, that looks in the growth in cooling energy demand in so-called cooling degree days. These are the days above the average temperature of a day above a certain threshold. And there you can see that, of course, it's especially the kind of moderate to northern zones that have a huge delta and increase. And I think it just has slowly become a big awareness that actually, if you look at the top 10 countries of relative change, Switzerland is actually leading this together with the United Kingdom. So we're transforming from a country that didn't really need to cool into a country that all of a sudden needs to cool. And of course, if you go to Singapore, cooling was always there, right? Buildings always needed to be cooled. And so there's been an adaptation in habits, in people, in building, in technology. But in Switzerland, this is not the case. We have building stock that is very old. So 65% is older than 40 years of residential buildings. So these are all buildings that were built and designed for a very different climate. Now we have this issue that with an increase of cooling and hot days, that after a few days already kind of the cooling reservoir of the building is depleted, but there's no active cooling systems. Right? So it means that in the future, actually our entire building stock is not really capable of dealing with this fact that we need cooling all of a sudden. So there's a huge problem. How do we deal with cooling in Switzerland? So this is the project we then started. We looked now this idea of an archetype. We didn't just do on a building level. We did on a settlement level. So we looked for representative Swiss archetypes, meaning we were looking for structures that were in their characterization representative of many, many situations in Switzerland. So here, for example, the urban archetype, that was an easy one. We were already working on Zurich Altstetten, which we have a lot of very good data. This is the typical mid-dense, mid-rise Swiss city, and that serves really well as an archetype. Then from the French part, we chose Echelon, which is roughly 1,000 buildings, which is kind of more a suburban archetype, a peri-urban archetype. And then, of course, a rural archetype, Airolo, which is a little, it's a bigger village, a little bit up in the mountains. So these were our representatives. And with those 3 communities, we had for 9 months conversations about their development and growth plans. How are they supposed and how they're planning for growth? Turns out that they really didn't have an idea. Well, Zurich has an URA, so to say, like in Singapore, which is called the Amt für Städtebau, which is trying to make plans how to cater for this. But already Echelons, they had one person in the community that kind of thought about urban. And then, of course, a village, it's all voluntary work, so they had no idea how they would develop. So we had long conversations to come up with certain development plans and certain development concepts. And this is the entire workflow that is behind. So we use those district archetypes, urban, suburban, rural, as placeholders for Switzerland. And then we developed 3 different development scenarios. One is business as usual, so things kind of grow uncontrollable and they go a little bit higher and lower. Then there's this idea of polycentric urban networks. This is actually a strategy by the federal office that is supported by some of the communities, which means, okay, Switzerland will not just be this kind of 3 big towns. They will be spread over entire Switzerland and they will be built up. Singapore has also, I think, concepts in this direction. And then, of course, it was post-COVID, or COVID was even running. Digitalization meant, okay, people will stay more at home, they will work from home, and there will be more remote work. And these different scenarios we basically filled into parameters. So the question of population growth in those 3 different settings, the question of occupant density, right, the square meters per person as just discussed, and building use ratio, so what is actually happening in the buildings that we built up here. Then we coupled this with 2 different RCP scenarios. RCPs are relative concentration pathways. These are climate models created by the IPCC. How climate could change, and this is kind of the lower bound and this is the higher bound. Of course, we want to know about the extremes. We want to know what is the worst thing that can happen. So this is the 8.5. It's probably unlikely that it will go that way, but it's kind of the worst case. And then we looked at this at different temporal scales. And the outcome is then a huge amount of scenarios and simulations, so 16,000 that were run then in parallel to see, okay, what happens if I look at those different parameters. Maybe just very quickly on the building retrofits. Of course, the building stock doesn't stay the same, it changes. So how does it change? There were 4 different retrofit scenarios included, what would happen, and they are all parameterized. So the most important part is the retrofit rate. So what percentage of square area would actually be retrofitted with different measures. And then you see how those pan out in terms of growth of GFA versus population growth over the different years in the different scenarios. So in most scenarios, there's an increase, but it can work very differently. For example, very clearly in the polycentric urban network, we have very distinct steps how the suburban areas have a much, much bigger increase. Versus rural is more on the decline in the classical scenarios as it is right now. Versus then in digitalization, this might flip, and we might even have an increase in GFA there. This then comes down to different use types. This is this diagram where we see how do the different use types change. On the urban, there's not so much change. We can see here that in the suburban, there is a bigger share, for example, in office and commercial, because there will be more of this activity. And in the rural, of course, the only thing which actually changes is digitalization, where people would stay in their villages, or even more people would be in the villages, and then they would work there from there. So what comes out at the end is the questions of heating and cooling. And what is interesting here is not only, the numbers actually not that interesting, it's the trends that we see. So and I will just quickly highlight those above. Of course, heating, we see that in most cases we expect that the heating energy will decline. So there's less heating consumed, but it's highly subject to the scenario. But then again, this entirely flips if you look at the suburban case. So our intuition would tell us, okay, everywhere the heating with climate change, so we need less heat. But of course, in the suburban, that changes due to the fact of a change in building typologies and a growth perspective. And you see a similar effect in cooling, that you have a very, very dependent on the scenarios, a moderate increase or a very sharp increase in cooling energy demand. And that tells you that basically if you plan for energy systems or any change in terms of infrastructure, then of course it plays a big, big role which scenario you actually look at. And you might be planning something that is then obsolete or not sufficient at this specific places. We also see the different mix that is then established in the different archetypes and different settlement systems, with the biggest change in suburban. So that's maybe one learning, that the suburban from this is the point where things need to be much more detailed and much more specific. And this is, if I would need to combine and collect the insights from this, urban areas face a rising demand for space cooling because of retrofit and climate change. And this is interesting, potentially matching space heating demand in 2060. So we're actually the first time we're on the same level, heating and cooling. Suburban areas exhibit a high variability, and this variability and the growth in floor space might have a negative feedback on energy saving and retrofit measures with a high planning uncertainty. Rural areas, rural communities are more stable. It is actually the biggest driver on the different factors, and especially on the cooling energy demand, is the non-residential buildings. That's also an interesting insight for us. What was most worrying is that the current slow pace of retrofitting and replacement of heating and cooling system per se is insufficient to reach the energy targets that Switzerland has set for itself. And this you can see from just looking at those three archetypes. So a second very different case study in a very different context was in Navi Mumbai, but also with respect to the question of growth. The main question here was, can we scale up, can we utilize these methods in a very, very different context where we obviously don't have all this fantastic data, where the stakeholders and the systems of stakeholders work very, very different. So if we do this fantastic research and all those great tool sets, is this only applicable to first world, high finance and high data availability, or could this be applied essentially anywhere? And this was the question here. And for this, we teamed up with a local team. Assistant Professor Chirag Deb at IIT, he's actually an NUS graduate and worked in my group in Zurich, and then became assistant professor there. And together with local stakeholders, the CITCO, City and Industrial Development Corporation of Maharashtra, of the state, where Navi Mumbai is located in, selected basically this area as an example. Okay, would we be able to kind of project the development and the different development trajectories of this area? And this is where we cut it out. This is one section of Navi Mumbai, and this is the closer district. And then we took this smaller district as an example to model. And the whole idea was, would we even gather enough input data, and could we even have a stakeholder-driven process in this? So this was the team. It worked for the first time with a remote team. So those 3 people Up here where the remote team basically gave support and training, and those were the people on the ground, Chirac and his 2 students, a PhD and a master student. And within 3 months, the aim was within 3 months to come to actionable information where local stakeholders actually could take decisions. That was the aim. Very sporty, but the idea that we had is, okay, there's this remote team that trains the local students that act as change agents that actually help and understand the situation. If we would go to Navi Mumbai, it would take us 1 year to actually understand what is even happening. Those people are very knowledgeable. So we would train them in using this tool set. This is the City Energy Analyst. This is one of our tools. I will tell a little bit later about that. And they would get training in this environment, and they would start gathering data, consult owners, developers, and stakeholders, and then pitch this and discuss that with the municipality, and ideally infuse this information in their design and development process, which happened to a certain degree, on different levels of control, let's put it that way. The idea behind that is that we just issued the CAA as a digital public good, which is an initiative by the United Nations that there's digital goods that should be available for everyone. And it's an open source tool, so this was basically our first tryout what would happen if we would do that. It's quite interesting was, okay, I mentioned before, if you want to do this, you need data, right? If you don't have data, you cannot model anything. So even though we have a pretty lean system, we only knew this part, right? We knew Switzerland. Well, Switzerland is very convenient. You have a lot of data on urban aspects from the government. It's all publicly available. Then you have open source, like OpenStreetMap, for example, OSM. Construction database, you have all those label and certification systems that give you all this data. So this is all nice, right? Our data world is nice in Switzerland. And as I mentioned, the question was, okay, what would happen if I would take this in a data scarce environment? Could I even utilize these tools? So the first 6 weeks, the 2 students really looked intensely into the different data, and they were able to uncover actually quite a bit, and that was really interesting. So there's still OpenStreetMap, for example, which is open source data, but there is also different regulations. There's adjacent research, but there also remained black data gaps, basically, where we were not able to obtain sufficient information, and we had to take educated assumptions how we put this into the models. But overall, we were very positively surprised. We thought it's data scarce, but it's actually not data scarce, it's data diverse. You have just a lot of different data and you need to search a little bit more, but there's actually quite some bit around even for Navi Mumbai. So in 6 weeks, they gathered this and then they run the different simulations for the city quad in Navi Mumbai, and the first thing they tested was kind of benchmarking. Are the buildings we're looking at actually within kind of the larger research and measurements of Navi Mumbai? And that was good. So we had quite a good fit with acceptation, except the residential, the high-income residential, which were way above what we expected. And that is because there are some buildings that have a very luxurious, even go higher than originally was intended. So there's some glitches in the planning that happened. They looked into how cooling demand would develop, also looking at the different climate change scenarios, and they could say, well, actually this part alone will have an increase in cooling demand dependent on the concentration pathways that under normal stance is not so significant, but if we take a prolonged, a faster development, then it will have significant impact. So the question of providing cooling. They did first examples of developing a district cooling network. So let's think about sustainable cooling. And within the tool, you can lay out and optimize these district cooling networks. Of course, that's very hypothetical. This is very unlikely that this will happen, just because the whole structure works very, very different. What is interesting for us was the question, well, if you want to decarbonize, could you do this with renewable energy? Which building types would you actually be able to supply with renewable energy? And that's quite interesting that for the low-income housing, you could actually have a very high renewable energy ratio, so you could completely decarbonize that. Why is that relevant? In Maharashtra, there's an enormous high carbon footprint on the energy grid. It's 750 grams of CO2 per kilowatt hour, which is factor 6.5 than, for example, Switzerland and much, much more than Singapore. So decarbonization means renewable energy. So this could happen for low-income residential, for example, also to a certain share with high-income residential, less than on, of course, hospital. That's a difficult thing. Commercial and office, even office, there would be a potential to do that. Now, of course, for the stakeholders, it was very interesting and relevant. Okay, what is the levelized cost of energy here? Would this be then cheaper if we would get this as compared to getting it from the grid? And what would be the emission intensity? Here you see the electricity grid, 750. And you see this is where rooftop PV is, somewhat around 55, 60. And even both in emissions as well as in costs, it's actually something that would be cost competitive over the lifetime. So if you think about 25 years of using solar. Then if you do this on a facade, which we also investigate, then this is not very cost competitive, obviously, in this surrounding. But there is a huge potential already now to decarbonize by renewable energy in this system as we have it right now. So what was the learning for us? Yes, you can do those things also with scarce and diverse data. It's a more effort to compile data sets to actually do that. This idea of local stakeholders as change agents was very interesting. We've now replicated this idea to Brazil. Next week, there will be a master student that has a dual appointment as a student and working in the local government, and she's doing the same exercise for 2 cities in Brazil. So this idea of having knowledgeable experts in this environment as these kind of change agents, that seems to be a way how this could be actually spread. It doesn't influence data availability, it doesn't influence necessarily the approach, the whole UBAM, urban building energy modeling approach, but it's the question of scale maybe and the difference in models you choose. At the end, we were not successful, right? That's maybe the bad part. And this is mainly because governance and governance structures you cannot understand in 3 months. So we were not able to really understand how the different decisions were made. And we learned that the city-level governments had not really full ownership. Even though they were responsible for the planning, they were not responsible for all questions related to energy development. So it would have had to go up a level on a state level. But we had some very, very interesting feedback to that. And what we also learned is, yes, we can have diverse data, but there's a high degree of uncertainty still. And we would, in the future, we need to go to such places and also do surveying, for example, measuring how high the buildings actually are, or at least gathering information. So manual surveying would have increased the quality of data significantly, but of course within 3 months that was not really possible. So that was an interesting learning, and since then we are trying to replicate this to very different locations. We are already in the topic, so the next question is of power. So we already saw here renewable energy as a point, and this is what we're doing at the Future Cities Lab since 4 years. Powering the City is actually the module, how it's called. And the question here is, okay, what is the impact of renewable energy? If we think about urban photovoltaics, what does that mean? And of course, yes, we know these facts. We know, for example, this is, by the way, a great study that looks at 176 cities in terms of the carbon emission tracking and what the different contributors to carbon emissions are in those cities. And if you just look at the bottom 3 rows, we see that buildings are massively part of those carbon emissions, which we already know from the beginning, but it's interesting to see how much that actually makes for different cities across the world. What is also interesting, and this comes again to the level of governance, is that actually local governments are the drivers of these efforts. So you see, this is by the Renewable Energy Status Report, over 920 municipal governments have implemented regulatory policies, financial and fiscal incentives, or direct support policies to decarbonize buildings through renewable power. And that is interesting for us. We see an interesting potential, and we want to know how does that impact the way how we think about cities. Again, I showed this. This is the carbon intensity of the grid, and if you compare this to the carbon intensity of photovoltaics at the latest iteration, this is data from Switzerland just a year, 1.5 years ago, we see the carbon content of monosilicium crystalline cell of 42.5 grams. Then, of course, you need to add maybe 25, 30% to the entire construction. So you end up maybe by 70, 75 grams. And if you see what the world actually does in terms of grid emissions, this would be maybe this color range here. And you see there's actually very few countries that could beat that, which means on 90% of this globe, photovoltaics would definitely be more an ecological version than if you take electricity from the grid. The only reason where this doesn't happen is for countries that are already quite fully decarbonized, the Scandinavian countries, Norway, for example. Switzerland is at the borderlining. Because if you drop, of course, below this content of carbon emissions, then it doesn't make sense to produce by photovoltaics because your carbon imprint will be higher. But you can say 90% plus is still affected by this. So a lot of cities could benefit from using photovoltaics. We've done a lot of research also on the building scale on building integrated photovoltaics, and there's quite some misunderstanding what that actually is, right? And I had this over the years, always in discussions, and I tried to formulate and try to define it actually with the help of the International Energy Agency, of the PV task, and I think that's important. The PV module, a BIPV is a PV module and a construction product together, designed to be a component of a building. Or negative, if a BIPV product is dismounted, it would have to be replaced by an appropriate construction product. So it's not you put some PV over a rooftop where you say, hey, I have a roof, and then I'm putting up some canopy, and then there's PV on top. It's really an essential part of the building. And this becomes interesting, why I will explain in a minute, but this is an example of one building in Zurich where you see this entire facade is basically made from photovoltaic modules, and it has become the photovoltaic skin. Right? It has become a skin that is energy generating, and you see how this looks then underneath. There's basically the raw roof is behind, and this is the outer layer. So very clear, you don't need a roof cladding, you don't need a facade cladding at this building, because you have an energy generating cladding. Now you could say, that's not a good idea, that's way too expensive, right? Why should we do that? And it's quite interesting that the perception of that is a very different one than the reality. So this is a recent research on European countries, and it depends on how you frame it, as always. But if you frame that a photovoltaic module means you're replacing a construction component, it also means that you can put this into the income breakdown. Right? So you have money you can generate by photovoltaic generation, electricity, very clear. But then you have the savings from the envelope costs. You're not building a roof, you're not building a facade, you just have this module. And then there's other small impacts on your cost and your income breakdown. And if you take this as your boundary, you can see that in almost every countries in the European Union, the levelized cost of energy, so the price of a kilowatt hour of energy generated is actually lower than if I would take it from the grid over its lifetime of 25 years, right? So against our understanding that this is a really expensive solution, we see that there is solutions where we actually come up with lower costs for energy than if we would just take this from the grid. I think this is really interesting because it becomes an economic perspective. The immediate question then, of course, is, okay, how much, right? If I would do this in the city, how much? This is nice for building, but if I would do this in the city, what would I achieve? And there's one important number that becomes really relevant, and this is the irradiation threshold. So the question, how many kilowatt hours per square meter does a surface receive in an urban setting? Think of a facade, of course, you have the angle, you have the overshadowing of buildings. Think of the north exposure, for example, in our climates, there's not much direct sunlight, there's no direct sunlight. And then the question is, what is this threshold to place photovoltaics? And if you say, okay, this is actually 1,200, then I don't put it anywhere because no surface in the city achieves more radiation than 1,200. But if I start to go down, 800, for example, this is already, this might be, it's for sure the roof, but then it's also the south facade. Then it becomes already more, and then you see this typical generation profile in kind of moderate climates. You have less in winter, more in summer. But then the interesting part is if I even lower that, so if I say 400 kilowatt hours per square meter, which means most of the facades except the north facade, I see that I'm already in a pretty interesting range. So this is again using the city energy analyst, simulating this entire city quarter for its energy demand, which is pretty stable, and then simulating the PV generation if I would take this irradiation threshold. So it's already very interesting. If I would utilize the surface areas available above 400 kilowatt hours per square meter, I would have a significant contribution to the energy consumption in the city. Now what the colleagues did is then put this in two different trajectories. Now you can say, well, I do this environmentally optimal, or I do this cost optimal. These are two different perspectives. Most people from economy would say, hey, let's do this cost optimal, right? We don't want to spend more money than that. And of course, cost optimal means that there's a certain learning curve, right? These systems might be affordable, but for sure they will get cheaper because they will, there's a learning curve and it will scale up. If I do this environmentally optimal, of course, I'm trying to replace as fast as possible because the grid carbon content will go down. So everything I do now will be immediately beneficial. Everything I do in 10 years, I'm already fighting against a lower grid content. And then it's interesting to see this kind of optimization strategy where I say I take two different lenses on this problem. This is how this then works. You basically dissect the city into different services that receive radiation. There's a radiation model behind it. And then you can see if you go for these strategies, you see that the optimal strategies cover almost all rooftops, right? That's very clear. But they also cover a big part of the south facades, almost all covered. And then to a large degree on east and west facades, nearly nearer on south. So this takes into account all the urban parameters such as overshadowing and all these different things. And if you see the different strategies and you look for the carbon optimal, then of course it rises very quick. You should do this fast, right? You should do this now. By 25, you already go to a high capacity and then you stay stable. Versus if you look at the cost optimal, there is a certain delay because you're trying to hinge on this learning curve, and then later it will be it's scaled up, but still it still goes pretty high pretty quick, which of course is clear when we look at the cost that I showed before. It's already important. It's already available in terms of cost. We did a similar study in Singapore or in Southeast Asian context, as you can see here. These are the grid emissions in different Southeast Asian countries as they are right now. And again, the question is, on which surface would I put solar photovoltaics so it, over its life cycle, has less carbon imprint per kilowatt hour than if I would take it from the grid? And this is this curve. Basically, this is the intersection between the horizontal, so the carbon grid emissions and the life cycle emissions of the photovoltaic, dependent on the radiation. There again is this threshold. Then what we did, what one of our PhD students did, is basically create a generator, a Singapore generator, surveying different block typologies, and then he created a very nice little tool that allowed us to generate different urban block typologies. And then we took a sample of those blocks and said, what would happen if I would employ these with photovoltaics? How much could I actually save, assuming that I want to stay in terms of carbon emissions below what I get from the grid? This is what you basically see here. The different block typologies would actually save you maybe 20 to 50% of your carbon emissions. And of course, it's very dependent where you are. In situations such as Malaysia with a higher carbon footprint, this is then, of course, more, versus in Singapore where the grid is already more decarbonized. It's still a significant percentage. And of course, it comes back to urban form. That is interesting. If you look, okay, what's the top performing block here? It's very clear that this is more a low-rise, mid-rise setting, which has more roof surface area and less energy consumption. So there is a clear link between urban morphology and this type of solar energy generation potentials. But it also shows that there is potential, even in a situation such as Singapore with a very vertical sun and already a decarbonized grid, to have a contribution. And last but not least, the question is, okay, now I generate all this electricity. This is great. What should I do with it? And everyone knows that, unfortunately, we use electricity when the sun is not shining. So in the evening times, and then I can have as much solar generation as I want. So it's a question of storage. And this is what the colleagues in a work package of our Powering the City module actually looked into. So this idea that actually electric vehicles could become a rolling storage for this renewable energy that is generated. That's not a new idea, that's or has been around for a while. It has not really worked for a long time because the cars and this kind of bidirectional charging was not ready. But this is actually demonstrated. We visited with our module in Switzerland, where this is in place, where people can hire, can rent these kind of electric mobiles that do this bidirectional charging. They take solar energy that is generated on the rooftops, store it, and then they feed it back into the grid or into the building if they need to. Right? So it becomes a rolling storage, and you combine two different things, questions of mobility and questions of renewable energy generation. So we looked at that also for Singapore, and the colleagues did, I think, something very innovative. They used large amounts of mobile phone data to look into this and to create kind of travel patterns, assuming a certain penetration rate of electric vehicles. And they basically generated certain location profiles that were able to derive from this mobility data, where people would actually go with their car and where they would stop and how long they would stop there. And then they assumed a certain charge of state. So if you're longer at a certain location, then your EV starts charging and you can actually load up solar electricity. And then when you use it or you go somewhere else, where electricity is needed, you discharge, right? And then it's quite interesting as a game to see, okay, well, how much could this actually contribute to different planning areas of Singapore? And here it's very interesting to see that, of course, a place where a lot of cars go in a fully charged state, for example, in the evening, they could contribute to the local energy supply. And this you see by the color shading. Some areas are not really getting any because the cars move there in an unfortunate period of time. But if you look at the different planning areas and you see the share, then in this very simple model, first estimation, we can see that there is a significant amount of local energy coverage through electricity that has been created and stored, created by renewables and stored in electric vehicles, and they could actually add to the energy consumption, energy supply of those different city quarters. So again, a very interesting link between different sectors, energy generation, construction, how people move in a city, and how they utilize these type of technologies. So summarizing, we can say urban solar has significant potential to contribute to decarbonizing through renewable energy. Of course, it's not a silver bullet. That's the disappointment we always get from stakeholders and say, yeah, but it doesn't solve, right? We need much more than that. That's true. But the future energy system will be comprising of different solutions and they all play together. So unfortunately, there's no nuclear power station in the future where we say this solves all of our energy problems. But solar can have a big share. And if you look at the price drop of solar that is happening, it's already the cheapest form of energy generation. The question is, will it become this also in urban context? What we can see is that all those benefits, economic and ecological benefits, are very dependent on local context, the city, right? Yield, solar yield, availability of solar radiation, seasonality and grid context as the most dominant factors, if this makes sense or not, right? So it's very specific. Urban form and topology dominate both energy demand and local generation capacity, so on both ends, the building as prosumer. What is very interesting for us as architects, I think, PV becomes designable. This is the first solar tower in Switzerland actually built 15 years ago. This is an entire solar facade. Every black panel you see here is a solar module. And they try to really push it, and of course it has implications on design. But this was one of the first high-rises that was completely clad in photovoltaics. And this is just one example. There's a lot of options you can design solar these days. So it's not, I mean, I'm at the Department of Architecture, so I have to defend that a lot and discuss a lot about the ugliness versus the beauty of solar. But I think that's not an excuse anymore. There's interesting temporal overlaps. So the next thing we're trying to look into is solar cooling, so how to use solar for cooling purposes. And as already mentioned, there's interesting options how to utilize other developments, such as electric vehicles, to improve utilization of solar energy by using them as a storage. There's some technical, some economic constraints, but we see now demonstrators where we see this actually works. So it's worth looking at. Last but not least, I want to talk about materials. This is a shorter input because this is a new field of our research that we're working on. So we talked a lot about operational carbon. So what does it mean to reduce carbon emissions by the operation of buildings? What about materials? We know that the better our buildings get, the higher the fraction of embodied carbon gets. And then it's a question, okay, we also know there's a lot of options around, but how does that scale? Again, this question, how does it scale? And I very much like this image. It's unfortunately not for me, but it's from colleagues which show that in the past we relied on carbon forming, right, terrestrial carbon, by millions of years. And this is what we've dug out over the past 170 years. And 270 years, and this has become, of course, our fossil fuels, but also all our construction materials. So this idea that we're actually depleting a certain carbon storage. So we need to reverse this, and we need to find ways how to actually deal with a carbon pool replenishment, and I think that's a fascinating idea. And buildings, of course, as the things that need the most material are number one in actually doing that. And there's a lot of development. It's quite exciting. And of course, these are the big construction materials. You can say, yeah, maybe I cannot use timber everywhere. But cement also, there's a lot of research that is curbing carbon emissions of cement, even to the point where cement and concrete can become carbon storage. There's a lot of sales right now. It's a very small amount, and you still have a lot of emissions in concrete. But there is a lot of research trying to make concrete active in carbon storage and carbonization processes, for example. It's maybe a little far ahead, but you know, I mean, carbon is the most used material on this planet, so every change of maybe 1 or 2% would have a huge, huge impact. Steel, there's not much to do. We cannot unfortunately grow steel, but what we see from northern countries is there's now decarbonized steel, for example, Norway, because they all use hydropower for that. Then you can say, well, it's from renewable energy, so at least the carbon footprint is much smaller. Then, of course, timber becomes more and more interesting because it uses per se much, much less carbon when you establish it, but also you have a carbon storage potential. And that is interesting, right? I'm not only using that with a low carbon method, I'm also storing biogenic carbon in my buildings. Of course, I'm super simplifying that because there's a lot of research how the deforestation and the management of forests is very dependent on what this carbon storage potential can be. You have examples where if you use bad ways of forestation and deforestation, your carbon content of timber actually becomes worse than concrete. So it like any time in research, it depends, right? But if you do it well, there's of course an interesting potential. We had an interesting, or we're still in this very interesting research project with our colleagues from material science that develop carbon negative materials. So the idea is that a material in their process is actually taking up more carbon that it is needed to produce it. And biochar is one example. It's a pyrolysis process where at the end you have a negative carbon balance. So this material actually sucks up more carbon. And of course, it's an interesting perspective. All of a sudden we want to reverse, right? We want to use more material, not less material, because we potentially could remove carbon from the atmosphere and package this in these type of products and materials. Of course, there's a lot of ifs and buts, right? Economic viability is one question, durability, all those things. I mean, just imagine the construction materials we use today, they have at least 50 years of advantage in optimizing a product. If you take an EPS foam, for example, there's been literally 50 years of optimization into it. Now we come with these type of materials, 0 years of optimization. So it's still a long way to go. The other part is bio-based insulation, which is very interesting. Hemp, straw, recycled paper, cellulose, all those things. Those are quite interesting. Maybe not in a Singaporean context, because most of them are quite sensitive to humidity. But I mean, in general, as a general perspective. So what we did, again, with the city of Zurich, this is the City 4D, this is called. This is the high-resolution city model by the URA of Zurich, so to say. So what they do is they provide a planning horizon. All the yellow buildings are the buildings that are already accepted and that will be built in the next 5 years. The blue ones are the ones that are applied for and might happen in a longer period of time. So this is the current state and the future state of Zurich. And that, of course, for us is already very interesting information. So this is Altstetten. This is the most dynamic part of Zurich. It's interesting. Zurich has very ambitious carbon reduction targets, way beyond just operational carbon. And of course, for us, it's great because it has excellent data sets, right? A lot of public data sets available that helps us to develop new methods in which we utilize in this. So this is Altstetten. This is a part of Zurich. And now, okay, we need to retrofit. This is very clear. So what would happen if we would retrofit with bionegative, carbon negative, or bio-based materials? How would this work? So we analyzed the city quarter about the building age, looking into the databases of the retrofit state and building age, and came up basically with a kind of rational retrofit process. So what would happen if we would address the buildings by age and have subsequent retrofit of this building stock? You can see here, as I mentioned, right, there's a big part that is older than 60 years. So very prone to retrofit. But there's also quite some new buildings that, of course, still run on the sources they have right now, and it will take at least 25 more years until they get a heavy retrofit. Then we create those archetypes. This time it's archetypes on the construction component level, so not from districts, but archetypes now on the component level. And then, of course, again, you build scenarios, the business as usual with a certain retrofit rate. This is the official governmental plan, Swiss energy transition. Retrofit rate of double. This is realistic. It's below 1% actually, 1.9% Swiss energy transition. And then what would happen if we want to electrify all buildings by 2040, so decarbonize all buildings? We would need to have at least a retrofit of 3.4%, right? So this is very much connected. So what would happen if we take these different scenarios and we say, okay, we do this with bio-based and bio-negative materials? What would the contribution be? And you see this is the optimal scenario, so the high retrofit rate of 3.4%, and the carbon storage potential of different buildings. You see a lot of somewhat in the low and the middle, And then some buildings that have larger development potential have quite some carbon storage potential per year. And if we take the standard retrofit rate, we see, yeah, there is a certain potential, but it's actually not so pronounced. You see only a few buildings have a smaller carbon uptake, carbon storage potential. And here we see two things. If we take different components, for example, wall, roof, and floor, then it's very clear that the walls have the most interesting potential, at least for this biochar, which is an insulation material. It makes sense that then, of course, the wall is more interesting. But it's, again, very, very prone to the bio-based material versus carbon negative. Bio-based material as such is only a temporal carbon storage because you're releasing carbon after its lifetime. Very clear, if you take wood and you burn wood afterwards, then your carbon is already emitted then after usage, so you're only temporarily storing, versus a material such as biochar actually actively stores carbon. It, however, has a higher carbon imprint in producing, but is able to store more. And you see how this enormously scales with the retrofit rate that we actually have. So if we do everything like we do now, well, nothing happens, right? There's not much of an impact, even if we have the nicest materials, right? So it only comes in combination with a higher retrofit rate that makes this very interesting. Another interesting insight for us was, well, materials is of course very important, but the building stock's already there. We need to retrofit it over a very long period of time, which means that the carbon balance only rises slowly versus the buildings already now consume operational carbon. They emit operational carbon. So even if I take the most ambitious rate, 3.4%, it still takes roughly 20 years until we balance out the operational carbon emissions versus the embodied carbon emissions. And that is, of course, very relevant if we think about strategies. Right now, we're all excited and hyped about carbon negative materials, but actually in the next 20 years, we still need to focus on reducing operational carbon because the buildings are already there, right? It's not, we cannot just change them so quickly. What is missing in this perspective is, of course, that the carbon negative material is only part of a lot of materials. So, of course, an insulation is just one part of a building assembly. So we're only looking at this part versus all the other emissions that appear when I have facades, windows, all this other stuff. So this is, again, an isolated perspective. And it's a first view, I would say, right? But it already shows us very logically that the operational emissions still become dominant or are still dominant until a certain time when the grid is decarbonized or the buildings are decarbonized. We can see if we take a very ambitious scenarios, we can break even to a certain amount, a certain time, 2040 maybe, in this example, with a lot of assumptions, of course, could be also 2050. Biochar is interesting as a material because it offers a much, much larger carbon storage potential as compared to bio-based materials. But as already mentioned, if the retrofit rate remains low, there's not much impact that we will have by even those more advanced materials. Okay, I want to quickly wrap up. I'm thinking I'm already taking over time. Apologies for that. But just on the very end, on the process, at the very last part, so, okay, what are ideas how to fuse this into decision making? And one important tool I already mentioned, I just quickly want to show it here, is this modeling, this open source modeling framework. This has been in development since 10 years. It's now used in 62 countries in very different projects. Everyone can basically download it. And the whole idea of this was to make this accessible and available to as many stakeholders as possible, so reduce the amount of input data that is necessary. Under the hood, there's a big bunch of models. Models of systems, for example, as you see here, building systems, but also larger scale systems. So physical models that simplify the systems at play. And of course, there's a lot of information that is context specific, grid emissions, for example, carbon content of materials. But yeah, it can be used for these type of exercises. And what we try to replicate in this, I'm not going through all of this, is basically this process I've been talking about is replicated in this tool. So you actually use it along this process. You start by creating scenarios where you have a lot of input data that you need to collect. You then forecast demands. You think about energy potentials. This gives you kind of the energy balance idea. Then you think about supply networks that can be planned. And then at the end, it can be optimized for different objectives. For example, for energy consumption or certain other elements. What we did in this is connected to different other simulation tools. For example, transportation with MatSim, which is a transportation mobility planning, Calliope, which is energy hubs, Nexus G, which is a grid scale simulation, and then NVMet as a microchromatic. But the whole tool is also core in different other programs. Cooling Singapore, for example, uses the City Energy Analyst as the energy core, and other endeavors that use this tool as it's a core that happens behind, and this is also nice. People just put this into their own tools and build up on this. There's a little commercial break. There's the user days. The CA user day is actually in 10 days here in Singapore, our first one in Singapore, where we invite people from Southeast Asia that use these type of models and tool sets, and they show what they actually do with these type of models. So on the website, there's some information. The whole idea is that as many people as possible use this and rebuild it and add to it and change it, so we can have a little bit more impact and we can distribute it at the end. But of course, this is still kind of classical modeling as you would see it, and of course also we think about things and methods to speed this up. So for example, using machine learning, one big challenge is how do I actually build those archetypes? How do I represent the city with only a few representatives in the city, right? This is a very challenging problem because you think of data of very different categories and domains. There's numerical data, building age, for example, the U values of construction. There's categorical data. Is this a use type of an office? Is this a building? So it's multimodal data that I somewhat need to use to build up representatives. How this is done normally and how we did it in the past is say, oh, I think this is a residential building and I'm adding some parameters that make this a residential building. But is this really representative? So an exciting avenue we're currently exploring is using unsupervised learning, so clustering, taking into account data from different modes, so categorical data, numerical data, to build up building clusters. And then we basically see that a city such as Zurich, we can pretty nicely define by 9 different clusters that are representative of the building stock in Zurich. And of course, these are all combinations of very different parameters. For example, if you look into the clusters, this is just from the perspective of non-residential users. You see that there's some buildings some clusters that are almost purely residential, maybe some other aspects of heat generation system, and then are very decisive on different use types. So use types still seem to be dominant, but there's other factors such as building form or heating system that play into this entire equation. So this is how we hope that for each city we can actually very fastly create a suitable set of archetypes that represents the city and can be used for this type of modeling. Another exciting avenue is to do it without models, obviously. A lot of you are working on this. So the question is, how can I use other techniques? How can I use image data, for example, to generate the amount of solar? This is a very nice work in our group that looks into how can I use machine learning techniques to identify suitable areas for photovoltaic placement without a model, just by a picture. And she's developed a very nice workflow that shows this works actually quite well and compares really well to the ground truth. So essentially it means that instead of modeling everything in high detail, there can be methods that extract this almost automatically from image data that is available. So again, something that is very data-based and data-driven. So last slide. Thanks for bearing with me. I think moving towards this kind of systemic design can provide relevant impacts and insights for decision-making. But of course, it requires that we think not only in this one domain, but we embrace a higher complicatedness, maybe in many cases, at least what I'm talking, maybe even complexity, but I'm not a complexity scientist. But it's interesting to identify these interactions. These interactions help us to understand what we should do. We have to change our way how we do this. This needs to be iterative. This needs to be in feedback loops. And we have to use this type of analytics for evidence and at the end. Computational tools and methods can help, and we're just at the very beginning. You think about all the methods of artificial intelligence, there's a lot more to come. It will be very, very interesting. And I strongly believe, but we have to always look into design for qualities and quantities, so this can only be complementary. And with these techniques, I still hope, I'm confident that we can design towards a positive building future, an urban future, and these tools and these approaches might help us on the way. Thank you very much.
Thank you, Prof. Arno. That was a very fascinating lecture. I would now like to introduce the moderator for the evening, Prof. Yun Chao. Prof. Yuncha is an associate professor with a tenure at DOA at NUS. He was the recipient of the Presidential Young Professorship when he was an assistant professor, and is also the founder and principal investigator of the Urban Climate Design Lab at NUS. Being an architect, urban climate researcher, and educator, Prof. Yunchao's teaching and research focuses on climate-sensitive urban planning and design for sustainable, resilient cities. He currently leads his research team in collaboration with MIT and ETH Zurich to conduct several studies on urban climate and future resilience for high-density cities. Prof. Yuncha also serves as the Director of Research at NUS Cities, Associate Director for Urban Climate, and Editorial Board Member at Landscape and Urban Planning. I would now like the audience to raise their questions. I'll be moving around with the handheld mic.
Thank you for the introduction. Okay, thank you for the very insightful presentation, and you really cover a lot of topics, right? From climate to building energy consumption, and from the operational carbon to the embodied carbons. So I believe you have a lot of questions, right? I would like to leave more time to you to ask the questions. Yeah, so who wants to ask the first question? The floor is yours. Okay, we have the first question. Yes.
Well, first, thank you for sharing, Professor Schleuter. And I want to ask the question is, how do you consider about the urban building energy consumption on the climate change? We can generate local waste data and add trees, and how do you consider about it? And a little question is, how do you consider about the validation in UBM and with real energy consumption data? Yeah, that's the question. Thank you.
Yeah, thank you very much. I think the first one was on vegetation and how natural systems are included. Do I get this right? So vegetation and natural systems, how this infuses, how this impacts energy consumption. Yeah.
Our first question is.
Take your time.
Yeah. I want first. We have several ways to promote our UBM, and we can try currently we use TMY data. Yeah. But actually we can use local waste, generating local waste data and to promote it.
Yes.
Promote it. And we also can consider about trees in our urban environments, and it's a second way, I think, and it's to improve it. And I want to know.
So basically, what's the impact of the microclimate, localized microclimate on the energy consumptions?
Yeah. So that's a very good question. What we do by standard right now is we are not digging into microclimate in our tool ourselves, but we try to make the link to microclimate, and of course it goes both ways. First of all, the microclimate, of course, is a very different one than if we take TMY files from an airport or some other weather station. It's very clear. So one is on the input side, and this is, for example, in Cooling Singapore, there is climatic simulation that then informs the microclimate and uses this as input data for the simulation. Then vice versa, the energy that is consumed in the building also is fed back into the environment. So it goes kind of both ways. But for this, you need the link to microclimatic simulation, and there's a couple of ways of doing that. Cooling Singapore has built this in under the hood. We have done this in different other exercises, for example, with NVMet. We had a PhD researcher that looked into this NVMet, and now we are hoping to team up with Prof. Yuncha to make this happen. So yes, that's an important factor. It then shows that the one is more impactful than the other. So of course, local climate files, local climate information can be very different than the overarching climate, but the flow back from energy into the urban canyon is mostly not so pronounced unless you're in a very, very dense and packed setting. So it's interesting also here to understand the mechanisms behind. Vegetation, we have in our newest model in terms of shading. So we can load vegetation to provide shading, and then it has implications on solar energy generation and as well as heating and cooling and seasonality, for example. It's not, again, not included in the microclimate. So evapotranspiration of trees and vegetation is not included. That is then again something that is more on the microclimatic end. Thanks.
And that little question is about the radiation. Yeah.
Radiation, yeah. So we have different radiation models in the CA. Right now we're using a model that is called DASIM, which you might know, which is an available radiation package. But we're currently also developing a new model which is faster and more cut to our requirements. Right?
Okay, thank you very much.
Sure.
Okay, yes, another question.
Thank you for the really detailed and interesting presentation, Prof. Arno. So my question is, number one, my eyesight, I felt like it was a bit of a test of my eyesight because I was struggling to see some. Your slides are very detailed.
Yeah.
But one thing I picked up was that a lot of your work was on projections, right? Projecting like what might different climate scenarios be and what are different projections for total, the potential of different types of climate materials that we might use in those different scenarios.
Right.
My question is, did you look at the limiting factors about, for example, let's say facade-based PV? What are limiting factors on us being able to achieve that theoretical peak like coverage? For example, if you look around Singapore, there are plenty of rooftops that have not seen PV deployed. So the potential is not there yet. So did your research cover that?
Yes, this is built in the scenarios. So for example, for the retrofit, there is then optimistic to neutral to negative scenarios where you assume that people are willing and informed and there's economic incentives to do so. This is the positive end. And then, of course, there's more realistic scenarios where you have other constraints. And as we try to package into the different scenarios, that's very important. I mean, it's actually not so easy to estimate which surface areas would be realistically available, right? You have to take a lot of assumptions based on knowledge, and because you don't know, it only helps you to iterate through different scenarios what would happen. And then you maybe understand the order of magnitude. So if we only would free 5% more of those available surfaces, where would we end up? So yeah, this is within the scenario making, and there's very interesting techniques to build these scenarios. Of course, talking to stakeholders is very important. We also had here in Singapore, we had some interesting roundtables on photovoltaics, and we got their very candid feedback. When this would be used and how this would be used. And very often, of course, it's not hinged to ecological questions, right? It's questions of economics, it's about logistics, it's things that do not relate necessarily to energy. But you need to understand those factors, otherwise you're off the chart. And what happens for our students very often, for example, is in the first student project they do in CA, they simulate solar radiation and they come back and say, this is amazing, I can supply an entire city. Because very often these assumptions are, of course, much too optimistic. But this is also where these new techniques, for example, this visual technique using image data, this can happen on the facades, but also on the rooftops. And colleagues here at NUS have done interesting work how to estimate solar potential from rooftops. So yes, this needs to be factored in. It's very important.
Did you model the impact of different interventions on the economic dimension?
So the economics is something we generally fall a little short because we like physics because we can project it, but economics is so dependent on so many factors. To date, we had a lot of students that looked into the economics, and we try to capture it sometimes as good as possible, but only if we have collaborators that help us with this, because we are not economics researchers. And there's the biggest uncertainty on economics. This can totally change, but it would be very important. I fully agree, but it's also really hard. We also, in Empowering the City, we try to kind of uncover the economic leverages, and it's not easy.
Talking about the building surface area for the BIPV, nowadays, actually, the rooftop is very busy. People want to put the PV panels at the rooftop. People want to put the urban farmings over there, right. Vertical greeneries. Yeah, what's your opinions on this? Yeah,
that's very clear.
Not only the economic impact, also the psychological impact. Right? Yeah, and we have a very nice building designs in Singapore covered by the vertical greeneries. Yeah,
true. So I remember when we started this in FCL a couple of years ago, there was a lot of discussion actually on the rooftops because of aquaponic farming. So everyone wanted to put on farms on rooftops. That has somewhat died down as a concept.
Yeah.
But so the first, also, I mean, if you walk around Singapore, you see all the rooftops covered in HVAC systems, and either they're that or they're Voitex. So I think there's a couple of answers to that. I personally think there's very interesting synergies. So almost every time there's a potential synergy, especially on vegetation and solar. And we had quickly, before this talk, we had a conversation, but we actually, there's the Water Research Institute of Switzerland has done exciting studies on this combination of would photovoltaics enhance biodiversity or not. And the interesting result is in the Swiss context, actually would. Because normally it gets very hot on the rooftop, which only allows a certain species to actually grow there. And if you actually provide shading, there's the potential to have kind of cohabitation, you could say, between photovoltaics and green roofs. So there's a small cooling effect, yes, but there's also shading effect for vegetation. On the facades, that might be a little bit more tricky. However, I've seen some interesting designs coming up where they also try to combine those two. And there's some interesting research going in this direction, combining that also in our group. I don't think there's really a shortage. Also for HVAC systems, you could imagine on all those buildings that you would put a canopy on top with enough space in between where you would actually be able to do both. So I personally think this is solvable.
So we can create a more building surface, right?
Yeah. But maybe interesting to that is really the question, which services are good for which utilization. And there's also some interesting work done in our FCL module. There might be some services that are really good for vegetation because they have, for example, the amount of solar radiation and the climatic conditions, which are not good for sort of solar photovoltaics. So if you think of the city as an aggregation of services, I'm pretty sure you can find services that are good for the one use versus the other use.
Okay, yeah, I totally agree. Yes.
Yeah, I would like to ask you about the heat generated by the solar panels. And solar panel absorbs about 70% of the solar light and converts about 20% into electricity, which means it actively absorbs sunlight and 85% is either deposited into the building or into the surroundings. So if you have a solar panel farm, then there is usually, you can absorb rising of temperature and basically, so that solves energy problem, but it introduces heating problem. Is that included in your simulation?
This is more about microclimate.
Right.
The impact, on microclimate.
Yeah, I would be interested in your perspective. So of course that's a pressing question, and we've addressed this in our research. But the short answer, it's ambiguous. It's not. So we don't have a definite answer yet. So we've seen studies, and we did a publication on this topic, where we actually saw some cooling effect, but because of absorption in the morning hours and a certain cooling down by a short amount, and then a little impact, a little rise in the evening hours. But it's very much subject to where this PV is placed, what the storage capacity of the material behind is, if there's an air gap, and how you actually depict the entire system, right? So it's a question, essentially a question that cannot be answered by modeling entirely yet. Maybe you know more about this.
In simple logical thinking is that the Earth has an albedo. It usually reflects quite a lot of sunlight. By placing, if you cover all of the area with a solar panel, then probably the Earth absorbs much more than its natural state. And as you point out, you have to increase the coverage of solar panels to transition into the renewal.
True, but it's still the question where this happens, right? And if you think about reflectivity of glass facades, you're in a similar situation, right? So it's likely that there will be a build-up, but I don't have a definite answer yet. It really depends on how you place it, how you ventilate it. And most likely in dense cityscapes, you would also not choose the lower regions for placing solar panels, because you try to have as much radiation as possible, which is rather in the upper areas. And then you, of course, have reflectivity, but you also have convection effects. So I don't have a definite answer yet. Right?
It also depends on the daytime or night times.
Convective cooling means the heat is deposited into the Earth.
So for example, PV panel will not do anything at night times for the air temperature, but daytimes maybe will increase the temperature. And also depends on the surroundings. If it's surrounded by all the high-rise buildings, then of course the reflection cannot be dispersed, right? Yeah, if it's the open space, then okay, maybe the impact will be smaller. Yeah, so it really depends. Yeah.
So I think we will see a lot of interesting research coming in this direction. And like I said, we had to end at some point because there's the right models are not available to depict this in a good way right now. But I'm also not a microclimatic researcher, so this is really something you and Zhao needs to answer.
Yeah, we're about to publish one paper regarding the impact of the solar panels on microclimate on UCHI, yes. So actually there's no impact on UCHI. Yeah, at night times the impact is very limited. Yeah.
All right.
Oh, yeah.
Thank you.
I'm really interested in the use of AI or machine learning. My question is actually, okay, if I want to use some specific model, or okay, there are a lot of options. I can get any result I want, like using machine learning. I could cluster something. I use different methods. The result may totally different. How can you believe the method you select is correct? So how do you know? Like the cluster you identify as typical for your cities. That's the first question. And also, if I use a generative AI for projection, so I cannot validate. So that's my concern. So I don't know how to figure out this issue.
Oh, that's a valid point, but also not only machine learning, also in simulation you can achieve everything if you want. Yeah. But you can tweak simulation to get every result.
Yeah.
So just if you use physics-based, you also get there, right? So this is a more challenging issue on the larger scale than on building scale, because it's really hard to get a ground truth. And what we are still waiting for, I mean, yes, you can compare certain models with other models that have been validated, for example, with real buildings. So what we did for the CA at the very beginning, we looked at the results of individual buildings and we looked how this compared to Energy Plus, which has been validated on buildings, for example. So you can validate with other models that have been validated in the best way. Also on a building, so we always have case studies, for example, on the district network. We had researchers from TU Munich that modeled an entire city quarter for district cooling and district heating, and they compared the measurement data for this entire district with the results from CA, and they were actually really close. But this might also be just a lucky break, or I thought it's probably a lucky break. So it's an important question, yes, on one hand, but on the other hand, I'm not so worried about the precision. For me, it's important that it covers the relevant effects, how things influence each other in a qualitative way rather than the absolute numbers behind that. But that being said, we still hope to have as many as possible areas where we have a lot of measurement data that helps us to compare, and this is still necessary and needed. It's just not so easy to find an entire city quarter that has been built, operated over a longer period of time that provides the data to you. Believe me, we've done a lot of attempts. Most often you get just aggregated data, like monthly aggregates, that doesn't help you with anything. So you need a high resolution building monitoring and systems monitoring over many buildings that allow you to make this attempt. But we just actually discussed that on microclimatic end. There's interesting hope with using localized data. And if you couple this with building energy simulation, building energy consumption data in a high resolution, maybe you can get closer. But this is an ongoing topic. I fully agree.
Yeah, maybe I just follow up your question and help all the students ask one question. Okay, so nowadays we have so many softwares and modeling tools, and for microclimate modeling and for energy consumption modelings, for renewable energy modelings, right? If we want to look at the coupling effect, then we need to combine all the modeling tools together. Then we have more options, right? And what's your opinions on this? Yeah.
Since day one, we're trying this coupling exercise. It's very challenging. Actually, the first project was with Jan Karmelit, where we tried to couple building energy modeling with climatic simulations. The problem is just the very different resolutions and time steps and the input data that is necessary. So we tried this really a lot of times, and it's just a very hard thing to do. It becomes extremely heavyweight at some point. So also the Cooling Singapore project combines a lot of models, but it becomes a very heavyweight exercise. You need supercomputing at the end to run all your models. So I tend to believe that I'm more interested in more specific model packages or model combinations that answer a specific question, and they can be rather lightweight and they can rather be fast. Again, I don't think it's so much about precision. It's really understanding the underlying effects. So what gives us more hope is really having more elegant, more streamlined, but maybe a little smaller in scope models that combine relevant effects, right? So I don't believe in the big world model that can do everything. Maybe AI will help us to advance in this direction, maybe. But then again, AI requires a lot of data, and cities are not really the place to get a lot of data easily and available. So,
Okay. Thanks. One last question. Okay.
Hello. I'm interested in the synergy of the different industries, or like the interactions between different aspects of the solution. So how do you make sense of the whole process?
in terms of how do I deal with the results?
Yes.
Okay. So what we try to do is to embed our stakeholders in this process. And every time we build something up in terms of scenarios, we want the input and we want them to take part in this exercise. And when we get the results, we want them to reflect and provide answers and insights on those results. But it's not so easy because many people in this chain are not used to this type of quantitative information and not to this process. So that's a second big part. Since years, we're trying to find process organizations that make this much more available. So, for example, our urban planning department also is very siloed, right? Green areas doesn't talk to urban design, doesn't talk to energy systems. And if you really want to do this in a holistic approach, you would need to have people from each of those teams in this entire process. And that is against the common way this is done right now, right? Because everyone likes their little piece, right? Everyone likes their little box they can think about. So my opinion is it needs also a radical change in how we do these processes. So what we're trying to establish now with our stakeholder in Zurich is to have a very different project organization where we say we get from each part, we get someone that is skilled, knowledgeable about these topics, and together we have kind of an integrated interdisciplinary team that looks at these things. And this is how I hope to get more traction on the stakeholder end. But it's still not so easy to convey this information. Most people, if they see graphs or big numbers, then they have no reference, right? What does that mean for me now? So it takes a lot of translation to actually do that.
Okay, thank you so much.
Yeah, talking about this, I have a question. Okay, I take the opportunity, to ask one more question. Okay, do you think it's possible to map the whole complexity? And if we want to deal with this kind of things, do we need to map the complexity?
So a whole complexity of a city?
Yeah.
The whole complexity? So with the means we have right now, I don't think so. But it will always be
like we have to deal with complexity, and so naturally we want to map the complexity, then we will be able to deal with it, right? But it feels like mapping the complexity is impossible. Yeah, and what's your opinions on this?
So I think with the means we have right now, I think it is indeed impossible. We have to take pieces of this complexity and take certain effects we're interested in, because there we can build models. I mean, essentially we need to build the models that are able to answer the questions we're interested in. So if we don't know the question and we want to do everything, there's no model we can build. But I'm by no means an advocate of artificial intelligence, but I think this might transcend our human intelligence. So what you're proposing, so maybe in a future state where we might not know how this happens because we don't have enough insight, but I'm hopeful that these methods will allow us to gain better insight about the complexities with a new set of methods. But maybe not tomorrow, but maybe, in the lifetime of your PhD students.
Okay, thank you. Let's thank Prof. Arno again, for the presentation. And Thank you. Thanks for coming.
Yeah.
Thank you, Prof. Arno and Prof. Yuncha, for sharing your time and for having this amazing session. Thank you, everyone, for participating with your questions.